Okay, so hello everyone. And for those who know me, you know I have a passion, it's called Splines and imaging. And so, you know, like talking about the title, from compressed sensing to deep neural nets. So I worked rather deeply when there was compressed sensing around to make a connection with splines. And when I finally got there, somehow everyone switched to deep learning. and so again, I don't give up. So I worked really hard to make a connection between deep neural networks and splines. And that's sort of the tale I want to tell you today. But in fact, you will see everything fits quite well. So I guess it will connect rather with the first talk this morning of Professor Seo. Variational formulation of inverse problems. And so here, when you do imaging, so you have, let's say, here a specimen, let's say concentration of a fluorophore you want to recover, and you have your measurement. Here could be a fluorescent microscope, which blurs the image, and you have additive noise. So you want to recover this unknown object here. Once you have discretized it, it looks like that. And you want to recover it from those noisy measurements. And so you all know that this can be actually recast as an optimization problem. So you can here have a data term. So we're trying to estimate a consistent solution. And here we're putting some regularization. And since Stan is in the room, we're using the gradient, for example, as a regularization operator. And well, either 1 or 2. So 2 is, let's say, the old-fashioned from the 20th century, and at the compressed sensing, and people doing TV have been promoting the use of the 1 norm, and this works very well. Okay, so but going back to linear inverse problems, so here's a little history. So we have a nilpost problem, and because you may have like a system that's not easy to invert. So what you do, you introduce here some energy function that would be the energy of some operator applied to the image. Think of the gradient, and so this here's a Tikhonov, and and so you can recast it like that. So you're trying here to match your reconstruction to the data up to some uncertainty here given by the noise. And you will search for the solution that minimizes this measure of goodness here that you have. And if you write it with Lagrange multipliers, you get it like that. So this is like the easy way where you have 2 everywhere so that you can actually solve it in closed form, and you get it like that. And now if you just reinterpret this equation, actually this transpose here is the back projection operator. And now the red here, you can call it filtering, and so that you have the filtered back projection algorithm. So that's very standard stuff. Now learning, okay, so now everyone talks about deep learning. Actually, learning is also an inverse problem, but an infinite dimensional one. And so here typically you have like examples of data points, and let's say here, for example, if I have a regression problem, but maybe only here a one-dimensional variable. So what I'd like to find here is a function that goes from RD, so Rn here to R, such that the function will fit the data relatively closely, but not too closely to avoid overfitting. And so here too, in the early times, here people have also, because it's ill-posed, of course, because you're in infinite dimension and you have only finite data. And so here too, people have introduced like regularization. And of course, the first choice here is also to put L2 norm. And you can use some operator. For example, you could use the Laplace operator and so to constrain the solution. And then you can actually reformulate the thing exactly the same way as before. But here now, okay, here's the data you want to fit, for this sample at xm, and so now you're trying to estimate the function so that this is this mapping, the learning mapping, and in a way so that you minimize this regularization. And actually, if you do the math, it's not too hard. There's a very beautiful theory of reproducing kernel Hilbert spaces, and so you can actually, that's relatively very nice result that tells you that the solution of this problem is actually a linear expansion in terms of kernels. And so in fact, what this tells you is that you're trying to solve an infinite dimensional problem, and in fact the solution lives in a linear combination of kernels. And so then you can just fit this linear combination to your data point. And so this, I would say, is classical machine learning before deep neural networks. Okay. First, I told you I was trying to make a connection with compressed sensing and splines. So, okay, so splines, of course, they live in the continuous domain, and so you need the continuous domain theory of sparsity. And in fact, there are some precursors. Jerome and Fischer, 1975, who introduced L1 splines, and we, in relatively recent work here, we kind of extended that to inverse problems, actually using total variation. Yeah, so total variation, I'm a fan. But you will see it's not exactly the same as Stan is using. In one, it's the same. So splines are analog but intrinsically sparse. And so this is a sort of formal way of defining splines. And I like to see them associated with some operator. So a differential operator, and maybe to take an example, let's think of the derivative operators. And what's also important, we have the Dirac distribution. And so we'll say that the function s of x, where x goes over Rd, is a non-uniform L spline. So remember, L is an operator with knots x of k here over some index set if this thing happens. So something quite miraculous, because you apply the operator to the function, and all what's left is a bunch of Diracs. Okay, and if this happens, you say, okay, this S is a spline. And maybe to make it concrete, think of a piecewise constant function. Now I'm saying this is a d-spline, like derivative. Let's apply the derivative in the sense of distribution to this thing here. And of course, you'll get a Dirac distribution exactly, Dirac impulse at the location of the discontinuities, and the height of the Dirac is exactly the height of the jump. Okay, so this defines splines. So now we can use that to do a spline synthesis. So now here, if we have this operator, the derivative, it has a null space. It's just the constant, because if you take derivative of a constant, you get 0. and so let's try now to resynthesize. So let's take this innovation. So the innovation of the spline is just a bunch of Diracs. And what's important here, you know the location of the Diracs. So they are the xk, and you know also the height. Now from those Diracs, you want to resynthesize the spline. So how do you do? What you need is what's the Green's function. So the Green's function is the impulse response of the inverse of your operator. So if you take the inverse of the derivative, it's the integrator. So the impulse response of the integrator is the Heaviside function. So this 1 plus here. And essentially what you have to do is just replace every Dirac by the Green's function. So if I just put Heaviside function every time there's a Dirac with the corresponding height, I am here generating something that is piecewise constant, and there's still like a constant here. Let's be a little more general. Let's go to a more general operator than the derivative. So you can also, actually this works for any operator that has a Green's function. And now the Green's function then is this impulse response of the inverse operator. We have the null space here, which we need to be finite dimensional. And again, here is the linear combination of Diracs to resynthesize this. Okay, so here, let's take a second derivative. What's the Green function of second derivative? It's a ReLU. Okay, so you'll see the connection with neural networks. And in fact, so it's a linear combination of Green's function located at those positions here, plus some things that live in the null space. Okay, so this actually technique is relatively general. It works for different kind of operators. But now I want this theory of sparse representation. So you know in the discrete domain, sparsity goes with L1. And, but we need in the continuous domain a counterpart of L1, and it's not capital L1, it's actually the space of bounded measures or random measures over Rd. And so this space I call M of Rd, and it's actually the topological dual of the space C0, which are the continuous functions that are decaying at infinity. But there's another way also to define this M, which in some sense is easier. So it's just the tempered distributions such that this norm here is finite. And so what is this norm? And so this norm in measure theory is called total variation, but it's not the same as stand. So it's the total variation of a norm, and it's defined by here, so with a supremum, and in some sense it's like the dual of the L infinite norm, but we're here imposing that the function is smooth, and here even a test function that is in Schwarz space S. And there's also this equivalent definition here. When I said it was the dual of C0, actually you can also take the supremum over C0, so that's the more standard definition, but you know that S actually is dense in C0, therefore we can use it like that. And here this norm is better because it's actually valid for any tempered distribution. Okay, so this looks a little theoretical, but what's important for us? For us, only one thing is important, that Diracs live in that space. Okay, so, and good enough, Dirac live in that space. By the way, Diracs don't live in L1. Okay, so that's the problem of L1. But now, if you're in L1, and if you're in L1, actually this measure norm is the same as L1. Okay, so it's a little larger than L1. So for L1 function, it's the L1 norm. And otherwise, it also includes Diracs and a few other things. Okay, so here's now our representer theorem for generalized total variation. So now we look at our linear inverse problem. Now here we have some linear functionals. And so linear functionals, this can represent CT, MRI, I mean any imaging or, you know, some acquisition system that just uses a linear process, but usually in imaging we like linear. And now the problem is we just don't have many measurements, so we just have M measurements. So it's ill-posed. So now what we are doing here, we are putting a regularization on the M norm of LF. Okay, so L is some operator that we like, that should impose some kind of smoothness. And so with Lagrange multipliers. So now L is an operator that goes with splines. Okay, so what does it mean? It has a Green's function and also a finite dimensional space. Then we have this GTV semi-norm. Here it's just, instead of having just F, is L applied to F. And the functionals now, they just mapping a space that, I mean the space for which this norm is well defined. I call this a native space into R, and there's a condition that this thing should be weak star continuous. And then we have this representer theorem. And this is where I'm making this link between splines and compressed sensing, because this is compressed, okay, only M measurement. We live in the continuum. And now the amazing thing with this problem, so it's in full generality, we can prove that the solution of these problems, actually, there's one twist, the solution is not necessarily unique. Okay, so usually people get scared away when I say the solution is not unique. Okay, but the solution set is convex, and the convex set is actually the convex hull of what's called the extreme points. Okay, so the extreme points are really like the points that are in the corners of this convex set. And now the amazing thing is all the extreme points of that problem, what are they? I think you can recognize this guy is a spline. Okay, so what this theorem says that actually the solution of all linear inverse problems with GTV regularizations are splines. Actually, the splines are the extreme points and are really the guy that are sparse. And so if I look at this formula here, you have a linear combination of Green's functions. For example, if we were using derivative, it would be steps located at some position xk, plus a part that is in the null space. Now, what's the catch? You don't know where the jumps are. Okay, so there you need to make an algorithm to find the jumps. Okay, so be my guest. Okay, it's just an existence theorem that characterizes a parametric form of the solution. And it just tells you, oh, there are less knots than measurements. And now there's also something very nice. Actually, this norm here is actually the L1 norm of the coefficients that are in front of the Green's function. So that's really, at the end, it's like a L1 recovery problem is just the basis function. They're adaptive. We don't know where they are. Okay, we know their form, but okay, so anyway, so this, and so it's very general because it says now the solution of all those problems are splines. Okay, oh, if I write it like that, it's true, but if I replace with any convex data term, it's still true. Okay, and so it's double, I mean, it's finding the location of the Green's function and also finding the weights. Okay, it's not necessarily easy. Now, examples of linear inverse problems. So here, this is the regularization that you people who like deep learning should like. Total variation 2. Okay, it's not exactly the same as stand, so it's one order above. So total variation 2, it's like this M norm applied to the second derivative. And here, second derivative, Green's function ReLU, null space 1 and x. And so it's exactly the example I was showing before. And so it means if you have any problem, so now it's in 1D of that form, any linear functional, so the solution, actually the extreme point of the solution will always be linear splines. Just, okay, theorem doesn't tell you which linear spline, so that's, you need to write an algorithm to find it. So other spline-admissible operator, in fact, it works for any derivative operator. It works for any ordinary differential operator. Now it will just be like exponentials. It works for fractional derivative, hence my first picture on my introductory slide. It works for Laplacian, like here you get polyharmonic splines. It works for this kind of operators, so it's Laplacian perturbed by the identity. And actually, this gives us Bessel potentials as kernels. And so that we call those Sobolev splines. So essentially, every time you have a differential operator, you can associate splines. Recovery with sparsity constraints. So, okay, this was a theorem. How do you do it in practice? You have to discretize. And so now here, we discretize like that. So this S now is a bunch, let's say, of expansion coefficient, let's say pixels. And now, remember the regularization was imposed on some operator acting on the signal. So the discretized version of that will be LS, which will give me this U, which I call innovation. But now I will use this innovation as a auxiliary variable, and so it will actually this then will map exactly into the discrete L1 norm. So if I write it like that, it's exactly the type of problem that people have been working in on compressed sensing for many years. And then if you write it like that, you can use augmented Lagrangian and a Lagrange multiplier alpha. So you can make this augmented version of the problem. So that goes with ADMM. So this is an algorithm that many people have been using in compressed sensing. So you have the auxiliary variable here, which is, let's say, this decoupled version of the signal. And then here you have the L1 norm here. And here you just have some terms that force Ls to be equal to U. Okay, and then if you write this down and you apply the ADMM algorithm, it's a very simple algorithm that will just alternate because it will first given U and alpha, so it's some initial guess of the decoupled version of the signal and some Lagrange parameters, it will estimate S. And now if you just do the math, actually you see that in fact it's a linear problem. And if you remember my Tikhonov slide, it's exactly the same operator. So I can actually borrow the algorithm from the 20th century. It's just the linear solver, which will actually do this first step of ADMM. And then I have an update of the Lagrange parameters, so which will give me the best alpha. And then you have to optimize for U when all the rest is fixed. But this actually decouples completely because the L1 norm is just the sum of the absolute value. And then it's given by a proximal operator. And you all know this function here. By the way, it's a ReLU and a ReLU here. Okay, keep that in mind. Okay, so it's again splines. Huh? Okay, so that's sort of the algorithm. Then you can apply that, and that was, I mean, this some years ago when we were applying like compressed sensing to MRI, and so if you do a L2 reconstruction, you get this kind of artifact that you had seen, I mean, to a much lesser extent than in the first talk, and if you do L1 or TV regularization, of course, it works much better. Okay, but this was the first part of my talk. Huh? I went from, compressed sensing to splines, okay? I think you are convinced I have a theorem. How can you go from compressed sensing to deep neural networks? Okay, so let's just look at the algorithm. Okay, let's just look at the algorithm. Actually, what are we doing? We have a linear step followed by a pointwise nonlinearity. Okay, now instead of ReLU, we're just putting this stuff here, but it's a pointwise nonlinearity, etc., etc. So now maybe if you want to make a connection with deep neural networks, convolution networks, you would like those operators to be convolutions. Okay, and so you can ask yourself, what are the problems in imaging where actually this thing here would be a convolution operator? And so this matrix, so you see with HTH, we call this A, that's the normal matrix. And so, our generic solver looks like that. And so we would like this actually this matrix, the red one here, to be a convolution. So, the LL transpose, remember that was a differential operator. That is a convolution, so that's not a problem. Now the problem is about the A here. When is A a convolution matrix? And actually, when A is itself, when H is a convolution, of course a convolution followed by the adjoint is a convolution. But maybe what you may not know, that if you have a Radon transform, actually the projection in tomography with parallel rays followed by the adjoint, this is also a convolution. That's the reason why you have filtered back projection. And if it's MRI, even with non-uniform samples, so even if you are collecting data in the Fourier domain, in fact, this normal matrix is also a convolution. And then you can either use FFT-based implementation, or that will justify actually that you have an algorithm that does convolution, pointwise nonlinearity followed by convolution, etc. And of course, many people had noted that in particular Laplacian, very famous with neural networks. And so if you take one of this kind of iterative reconstruction algorithm, and now if you unroll it, so write every iteration after the other, you always have this sort of linear step, pointwise nonlinearity, linear step, pointwise nonlinearity. So let's just be a little bold. Let's say, instead of taking the things that are given by our theory, let's just try to optimize everything by just doing a neural network, and let's just try to optimize the neural network so that it solves the inverse problem. And so it's not so recent anymore, but okay, time flies. But so there was an appearance of deep convolution networks. So this Jin, I must say, is not our first speaker, but is someone who is somewhat related because he's also Korean, is a guy who was a postdoc, Kyung, who is his last name in my lab. And I was very fortunate. He absolutely wanted to work on neural networks, so I let him go. Of course, I was more a theory guy, but I said, okay, go. And in fact, he had the idea that we saw in the first talk that we could train maybe a neural network now to take this first filtered back projection or this, like coarse linear reconstruction, but that has is in the domain of has the size of an image, and then train a neural network so that it would correct the artifact, exactly like he explained in the first presentation. And so Jin proposed to use a UNet, also with a skip connection, like we had seen this very magical thing, the UNet, the skip connection. Actually, why you need the skip connection is because neural networks have a really hard time to learn identity. That's the very profound reason. So here you train actually the neural network to be a perturbation of identity. But anyway, okay. So here's the UNet, and then you apply it to reconstruction. So here is a CT image, filtered back projection. So that would be like, standard reconstruction, but it doesn't work very well because we're subsampling by 7. So we're in the sparse view scenario. So now, if we use compressed sensing and all the machinery developed by Stan, we get, 5 dB improvement. So that's, what kept compressed sensing people very happy for many years. And then here come the neural network guys. In 6 months, they add another 5 dBs. So applying a neural network, you get as much almost as, you get with total variation, okay? And I mean, we were very happy. We published that, and I'm even more happy now. Okay, so this I must say, I mean, this paper. Okay, we're kind of lucky because we were among the first to do that. We also have a theorem that justifies the use of a convolution network, with radon transform, MRI, etc. But why is this paper quite popular? Because it's actually the baseline of neural network. So everyone is beating it. So we went 5 dB, but now everyone is improving on those 5 dBs, but not by so much. Okay, so we did the best. So we are kind of baseline here, and so which is attracting some attention to our work. But I must say I'm more proud of the theorem I showed you before. But anyway, okay. So this works quite well. So here, if we have a reduction by 20, it's also you see that the neural network reconstructs much better. But they're also like, you have to be careful. Okay, so it may sometimes forget of little little things. So there's also some controversy going around the use of neural networks for image reconstruction, and so there are also adversarial things. So it's not super robust, but certainly if it's well trained with the right data, it works very well. But be careful if you apply it to the not right data. okay, which may be real data, but you know, then you have no guarantee whatsoever. But okay, it's amazing what it does when it, I mean, it's applied in the right way. Okay, so you say, okay, well, I made a connection with deep neural networks, but where are the splines? Okay, where are the splines? They're back. Actually, from now on, I will encourage you to call those deep neural networks actually deep splines. But it's not a joke, actually. Actually, it's based on the theorem. Okay, so, I mean, people, you have seen these neural networks, and people have, you know, during 50 years have tried all kinds of activation. Somehow, in recent years, this guy has emerged as one of the best, and it's the ReLU. And it works very nicely so that without dropout, with dropout, they're easier to train. So that's the pioneers, Lequin, Bengio, Hinton, had reported that, gets state-of-the-art performance. But now, what a few people have noticed that actually the output of the mapping, so a neural network makes a mapping from, let's say, RD to RD prime. Now, the mapping that such neural network make is actually continuous and piecewise-linear. And so that was even noted by Bengio. There's a very nice paper by Strang in Science News, 2018, where he actually explains to you where neural networks are splines. So if you don't believe me, ask Gil Strang. Actually, even ask Ingrid Dobeschi, and she agrees, okay? So I have like important people that are saying that actually there's a relation with splines. And in fact, there are also people like Poggio at MIT. It's just because you're like putting splines after splines, so it's like hierarchical splines. So let's look at the deep feed-forward deep neural networks. So we have a bunch of layers. I call them L. And now we have, for every layer, we have a number of neurons. So I call N0, N1, etc. We have like those two indices. L is for the layer, N for the neuron. And we have an activation function. So every neuron is, let's say, a ReLU. But, and then, in fact, what the neural network is doing, like if you have those arrows, is just representing an affine transformation. So it's putting linear weights, and there's also like usually a bias in the ReLU that adds a constant here. And then you have a nonlinear step here that is just this activation. And then if you look at the neural network, what it is, it's a linear map followed by pointwise nonlinearity sigma, just a vector, but pointwise, followed by linear, followed by nonlinear, followed by linear, etc. So we've already seen that. Okay, so what's the relation between with splines? So what is a continuous piecewise linear function? This is a continuous piecewise linear function. Okay, it's a spline of degree 1. But you know, how can you describe it? First of all, there are some knots. So we can form a partition of the axis here. So just in the segment, the interval between two knots. And now in how do you define this function? So in every interval, this function is a straight line. Okay, so it has ax plus b in every interval. But the non-trivial part is actually it's connected in a way that keeps continuity. Okay, so that means actually the function, the global function is continuous. So it's continuous and piecewise linear. And so that's really what makes it a spline. So you can, that's maybe not the way we like spline people to represent splines. We much prefer to use represent them using the Green's function like I've shown you before. And now this thing here is a ReLU. Okay, so you can actually represent those guys as a linear combination of ReLU. So can we do that in higher dimensions? Sure. Now we can take the domain, you know, like have polytopes here, triangles if we're in 2 dimensions, and define a partition. And then when do we say that we're continuous piecewise linear? we need the function to be globally continuous, and we need every piece to be linear. Okay, so now it's just, that's the equation of a linear, actually is an affine transformation, because we have also this bias here. And now if we have a vector function, vector valued function, so with several components, actually we will say that this multivariate function is continuous piecewise linear if every component is continuous piecewise linear. Okay, so that's continuous piecewise linear. Now there's an algebra of continuous piecewise linear functions. Any linear combination of continuous piecewise linear function is continuous piecewise linear. It's obvious. What's less obvious is actually the composition of continuous piecewise linear function is continuous piecewise linear. Okay, and so actually this is the secret. And actually the proof is very simple, because if you compose linear with linear, you get linear. If you compose continuous with continuous, you get continuous. Okay, so essentially that's the proof. And actually now if you do a max of continuous piecewise linear functions, it's still continuous piecewise linear. If you do a min also, if you do an average also, okay. But that was the, so if you do all kinds of things, actually if you do the kind of things you do in a neural network, if you're just obtaining, preserving this continuous piecewise linear property. So here's a neural network, here's the composition, so linear, let's say ReLU, linear, ReLU, piecewise, etc. So every scalar activation function ReLU, I think I've been talking now half an hour to convince you that this guy is a spline. Okay, it's a continuous piecewise linear. Okay, each layer, now each layer, if we have here the F, just this F is just the linear part, composed by this continuous piecewise linear, is continuous piecewise linear. And then if I just compose layers, it stays continuous piecewise linear. This holds true also if you have max pooling or things like that. It doesn't destroy the property. And it actually also remains true if instead of a ReLU, you were doing something more complicated, but that's still continuous piecewise linear. Okay, so you get splines. So I'm not making it up, okay? A neural network actually generates a spline in very high dimension. Continuous piecewise linear function further properties. So those guys have universal approximation theory properties. In fact, I was working around Paris, like next Beaubourg, and I saw this continuous piecewise linear statues that impressed me, so I took some nice photos. Actually, it also goes the other way around. That's not so much known, but if you have a continuous piecewise linear function, you can also implement it with a deep neural network. You just need to put actually log of n. So n is the dimension of the problem layers. If you put so many layers, you can do it for any continuous piecewise linear function. Okay, and since continuous piecewise linear function can approximate anything, you just have to put enough facets so they have really universal approximation properties. Okay, so I told you that neural network is a spline, so now you can call them deep splines because it's continuous piecewise linear, but let's go a little further, okay? Why do people use ReLU? Okay, because let's say they work well, but let's be a little bolder, okay? Let's say, okay, we don't believe ReLU is the best. Now let's keep the activation open. Okay, so now we have the deep neural network. Every neuron has an activation, and now let's optimize the shape of the activation function. So maybe this way we can beat ReLU networks. And then you tell me, hey, this is a ill-posed problem, okay? Because I have finite data, every activation has infinite parameters. I mean, this thing doesn't work, but we know regularization. Okay, so let's now train our neural network and train all the nonlinearities. And how do we do it? Okay, we need to constrain the activations. Should not penalize simple solution. You know, linear, that's perceptron. So we should allow for the linear. So somehow we should not penalize linear. So let's say taking a second derivative gets rid of linear. So we should be differentiable in order to be able to do back propagation. So therefore, you know, it's good that our activation be differentiable and should favor continuous piecewise linear, because that's, you know, that what everyone uses. Okay, you guess what is the good penalty? Total variation. But second total variation. Let's just impose a second total variation on every neuron. And then we have actually a space. This is BV2, is the space of all functions whose second derivative, the M norm of the second derivative is finite. Okay? And here's the theorem. I call this a representative theorem for deep neural network. I mean, now it's published in Journal of Machine Learning Research. So you have now a neural network, and now we are like optimizing any cost. So this could be some kind of cost for goodness of fit, some regularization like weight decay, let's say L2 norm of the weights. And now we just add a total variation 2 over every neuron, okay? Because we have layers and we have also neurons going like that. And now guess what's the solution? Now the global, the optimum of that problem here. So usually people have, they don't use this, okay? This you don't have. I mean, this is what I added because I want to optimize also the neurons. And now what is really remarkable, the solution of that problem, every neuron is a linear spline. But okay, it's just a theorem. It doesn't tell you how many knots. It doesn't tell you where they are. Okay, still you have to do an algorithm to find that. And now what's the outcome here of this representative theorem? So every neuron that will have a certain number of knots, the location of those knots will need to be optimized. And then actually what's also nice, there will be like a sum of ReLUs. There will be a coefficient in front of the ReLUs. The total variation 2 is actually the L1 norm of the coefficient in front of the ReLUs. So it gives you a very natural L1 criterion to optimize. But now all this becomes data dependent. And link with L1 optimization technique, yeah, because we're still like minimizing the L1 for each neuron as a sum of those ReLUs. Optimality results, so how does it go? Actually, there's this theorem here that tells you if you're solving an interpolation problem with this D2 condition here, actually this has a solution that is a non-uniform spline with no more than M-2 adaptive knots. And this is somehow, you know, derivative of the theorem I showed you before. But now, how would you connect those points? Okay, the classical solution is like that. That's also the Sobolev solution of spline. This is the solution that will minimize the energy of the L2 energy of the derivative. Okay, and so that's the normal solution. But now the one that's given by our theorem, don't know if you saw it. Okay, goes through the same points as only one knot. So it's much sparser. Okay? And so there you can, let's say, contrast the old style math, like the theory of reproducing kernel Hilbert space, with this kind of result here, which is more like of the same flavor but over non-reflexive Banach spaces. Okay, and here, if you have the space of measures, it will really enforce sparsity. Okay, so now discussion. Now, global optimality with spline activation. So that's what the theorem says. And it's sort of backward compatible with actually what people do, because the standard ReLU network, there's just one knot per neuron. Okay, so it's compatible. It's kind of, you know, if you crank up the regularization very strongly, you just have one knot. By the way, if you crank it out a little too strong, even the knot goes away. Everything becomes linear, and it all collapses to a perceptron. Just a linear thing, okay? So linear regression. A state-of-the-art ReLU network. There's something that's called, well, one ReLU plus a linear term. So that's called parametric ReLU. People have noted that if you add a little thing on the ReLU, it works better. And there's also some work by some other people here had proposed, like putting, you know, linear combination of ReLUs, but a fixed number of such. And they have reported that this usually helps you to get slightly better performance. Okay, deep neural splines continued. So key features here, we have direct control of complexity. So this lambda parameter makes it, you know, more or less simple nonlinearities. In fact, when the knots disappear, at least formally, the neural network collapses. So it becomes, you know, you get rid of layers. I mean, we haven't implemented it, but the theorem has the ability to get rid of layers if there are too many. And generalization, so it works for all kinds of cost functions. It also, the result is still true if you fix some nonlinearities and you just optimize over, you know, a few ones that are left open. And if you use any like function of total variation, it's still correct. And so now, of course, there are some challenges. It's a much more difficult optimization problem because it's harder than training a standard ReLU network, because you also have to put more ReLUs, determine how many there are, etc. And you need optimal allocation of cost, etc. And also finding the optimal trade-off between having more complex activation or more layers. Okay? Actually, what we found in our research, we gain the most when we have more simple networks. Let's say, for example, you had like 2 layers. For 2 layers, wow, it works really well. If you put zillions of layers, I mean, the neural network is so rich that it probably doesn't need that. But I mean, there's hope here that you can make simpler networks and more interpretable networks because it can also design its activations. And so we are, of course, in need of training algorithms. And so that's essentially the end. And I have to thank many people for this work. So let's say this is more like lots of work for the future, because we have to design like algorithms that can, in fact, optimize the neural networks that we use to solve our inverse problems. Okay, thank you very much.